So, any questions from the last class?
No, sir.
Okay, this thing we did last time.
Yeah.
So, this is a constraint equation, the length of the string. So, you get the length, right?
Yeah.
Mark it. X1 minus c is this length. Okay, and then x2 minus xc is this length, right? Sorry, that is xc.
Yes.
No, that is xc. So yeah, this is x2 minus xc. Okay. Okay, and this length is xc and this length is x2. Right?
Yes, sir.
So there are 4 lengths. 1, 2, 3, 4. Okay. 1 xc is cancelling. So we get x1 plus 2x2 plus minus xc equal to L. So if we differentiate, we get this relation. AC equal to A1 plus 2A2. Okay. This is perfectly fine. There's nothing wrong with it. So basically there are 3 quantities, right? Acceleration of M1, M2, and then the acceleration of the pulley C. Okay, acceleration of M2 is same as this acceleration of this second movable pulley. Okay, so that's not a thing. So there are 3 independent movements. One is M1, M2, and then the pulley C. Is that right?
Yes, sir.
Okay, and there's only one constraint, which is the length of the string is constant. Okay, so we get one relation which will connect these 3 quantities, A1, A2, and AC. So if we fix 2 of them, the third one is automatically fixed. Okay. This relation is constraining. If 2 of them are fixed, then the other one is fixed. Okay. But for example, this one, here there are 2 independent movements, 1 kg and 2 kg movements, x1 and x2, and there is one constraint. So we get one relation, one constraint relation which is relating A1 and A2. Okay, so if you fix one of them, the other one is fixed. Okay, here you have 2 quantities and one constraint. So if one of them is fixed, the other one is fixed. Here we have 3 quantities and one constraint. So if 2 of them are fixed, the third one is fixed. Right?
Yeah.
Okay. So similarly in this problem, what are the constraint here? In this problem, the length of the string is constant, right? There's a constraint.
Yeah.
Okay, here what is the constraint? Here the constraint is x and y will form right angle triangle with h as a third side. That is the constraint, which will not change. Okay, x and y will always form a right angle triangle with h as a vertical length.
So yeah, h will not change.
So this is a constraint in this problem.
Yeah.
Last time we started this problem. You remember this problem?
Yes, sir.
Okay, so this yeah, so this bottom one is fixed. Okay, so this P is going to slide down, and A will also move. A could slide on B. Okay, so that is possible. Okay, so one way to solve the problem is to use a frame fixed to the ground. You can take a frame here and then solve this problem. So with respect to this frame, let the acceleration of B be A. Okay, and let the acceleration of A be A2. Okay, and just give me the name. And this is a free body diagram of the wedge B. Just check whether it's correct. We just got a mass mg and the normal reaction just coming from the block A on top of it. And the normal reaction, because of the contact between the B and the wedge, fixed wedge, these are the 3 forces. Right?
Yes, sir.
And there's nothing else. And is moving on with an acceleration here. So that will give me this equation. No, that will be this equation, right? This blue one. Okay, mg n sin theta. N sin theta will act downwards. Is that right? N sin theta will act downwards here. That is one, this one, which is equal to, and then mg sin theta is downwards. These two will give raised to m into a. Okay, this is one equation. And another equation I can write from this one. See, let a to be the acceleration with which it's moving downwards, and there cannot be sideward movements of this block A with respect to this earth frame, ground frame, because the forces acting on A are what? mg and normal reaction, right?
Yes, sir.
Is there any force acting in the horizontal direction? There is no friction. The whole surfaces are smooth. So only two forces, and they are in the vertical direction. So there is no force in the horizontal direction, so it will just move down with respect to the earth. Okay. It will move down because B is moving down. So A will move down. Okay, for that this will be the equation. Yeah, and the contact between this A and B is not lost, right? Okay, so the vertical acceleration of B should match with the vertical acceleration of A. B is accelerating in this along the plane downwards. So this acceleration will have two components. One will have horizontal component, other one is the vertical component, right? Okay, so this vertical component of this acceleration is the acceleration of B vertically downwards. So that acceleration should match with the acceleration of A because the contact between A and B is not lost. Okay, so A2, this angle is theta. So this angle is also theta. Alternate angle. And this is 90 minus theta with the vertical. Right? So A sin theta is the vertical component. Is it clear?
Yes, sir.
This component is A sin theta. Okay, so A2 is A sin theta. So from that, I can have a relation like this. A normal reaction, I can put it from here, from this equation. So if you use this thing, you'll get the value of acceleration as this one. Okay. So what is actually happening is when the thing is going down, see when B has come here, if there is no sliding between A and B, then A will remain here, right? So E has moved horizontally. Okay, but there is no horizontal acceleration of A. So what is happening is A is actually slipping. It is slipping and it's coming here. Okay, so that effectively, with respect to the ground, A is just dropping down because it is slipping on this surface. Got it? When B is going down, A is just vertically coming down, but B is coming down and moving towards left. So to avoid that moving towards left along with the B, A will slide towards the right on the B. So A is sliding towards right and then moving down. This sliding towards the right is with respect to B, but with respect to the ground, it is not sliding. It is just dropping down vertically like this. Right? That is the interesting point of this problem. Okay, and B is moving down, A is coming down without any horizontal motion. That is possible because A is sliding on top of with respect to B towards right. Is it clear?
Yes, sir.
Okay. Another important to realize is the vertical component of the acceleration of B is same as A2. Okay. Try this one. First, see how many things are moving. Movable pulleys ABC. Okay, 1 kg each. B and E are fixed. Are you understanding?
Yes, sir.
This is a constraint equation.
Sir, 6.5 Newton.
Okay. An acceleration of A. You can find accelerations, right?
Yes, sir. G by 3.
Of which one? Everything, is it?
Sir, B. AB.
Okay, upward or downward?
Um,
Okay.
Downward.
Yeah,
Upward.
I'll tell the method. The constraint equation is clear, no? L equal to 2xc.
Yes, sir.
Okay.
Yeah, this
The yellow length is 2xc and the blue length is xc. And this purple one is xc. Okay, so from this you get relation. And then this is the free body diagram. Okay. Yeah, I'm assuming everything is moving down. So the acceleration is downward for everything. So one of them will turn out to be negative. Okay. So and this tensions are clear. No, there is only one string. The tension is T throughout commonly. And for A, one tension is pulling down. B also one tension is pulling down. C, only the mass is pulling down. Okay. So you get these three equations. Okay. And there are how many unknowns? Tension and then three accelerations. Four unknowns. Four unknowns and four equations. So you can solve to get this one. So AC is moving up. Okay. And A and B are moving down. Right? That's possible, no? See, when AC is moving up,
Yes.
so the string will slack like this. Okay, this slackness I'll transport here and then move this pulley down, not fully. So some more slackness will remain. So that slackness I'll transport it here and then move the pulley B down. Got it? No? Is that right?
Yes, sir.
Okay. What about this problem?
Sir, I've done this in class.
Okay. Fine. The free body diagram here. What is this force R? This force R. What is this force?
Sir, which one?
This force which I marked as on the monkey here.
Okay.
This force R. This one.
Yes, sir.
What is that force?
Um,
See, the monkey is climbing.
Normal.
It's not actually wrong, normal. That's why I put it as R. Otherwise, you put it as N. It's a reaction force. The monkey is going up by pulling the string down, right?
Oh, yeah. Yeah.
So,
So,
if we draw the free body diagram of the string or the rope, there is a force acting on the rope which is R downwards. And by Newton's third law, this force is created on the monkey. So the rope will exert a force around the monkey. So this is a reaction force.
Yeah.
Okay, this is the only catch. And then this tension component, the vertical component, that should not exceed 40. That's another relation. This one you did.
Yes, sir.
So what is the acceleration along the groove?
G sin 30 na.
Okay, you might have seen the solution. So this acceleration is given, right?
Yeah.
Along the groove, G sin 30 into sin 30. Okay, you
Yeah.
have to understand this, how he's getting this one. So how do you explain this one? Okay, what are the forces acting on this mass? Whatever is it? There is a cylinder here, right?
Yeah.
So what are the forces acting on it?
Sir.
Weight, right? And
Yeah,
some,
weight.
and some normal reaction.
Normal force.
And what is the component of the force which is acting along the plane?
G sin 30.
Okay, the normal component, the normal force will not have any component because it's perpendicular, right?
Yeah.
Okay, so only the mg will have a component along this direction of motion.
Yeah, so the component will be mg sin theta, right?
Mg sin theta, right? So to understand that,
Yeah. Yes, sir, understood.
see, this is the direction of mg, right?
Yeah.
Okay, so this component is mg sin 30 because this is 60, right? So this component is mg sin 30. It is cos 60 sin 30. Is that clear? I can split like this and then a normal component mg cos 30. Okay, so along this plane it is mg sin 30. Is it clear?
Yes, sir.
Okay, so that vector I can transport it parallelly here. It's along the same plane, and this angle is again 60 degrees. Okay, so this again I can split into two components, one here and one here. Okay, so this component is mg sin 30 into sin 30 because this is 60. It is cos 60. Cos 60 is same as sin 30. Okay, so the force which is acting along the line of motion, direction of motion is mg sin 30 into sin 30. So acceleration is this divided by the mass. So it is g sin 30 into sin 30. Okay.
Yeah.
Okay. But you have to understand this. Okay, this is x and this is the force. This is making angle theta, right? So the force along this direction is f cos theta.
Yes, sir.
Okay. So if I take a direction like this, which is making angle theta by 2, can I do this one? Can I first take the component of this force along this direction? That will be f cos theta by 2.
Yes, sir.
And again, I have to take one more component along this one. So it will be again cos theta by 2.
Okay.
So will this thing be equal? It is not, right?
Yes, sir.
Okay. So whenever you do this thing, you should make sure that the other component, which is being left out, that should be perpendicular to this line. Okay. But here, when I split like this, one along this one and one along this one, okay, this component is not making 90 degrees with this line, x-axis. It is making some angle. So the effect of this will also be have to take into account. Understanding?
Yes, sir.
This f I split it two components, right? F cos theta by 2, and then in perpendicular is f sin theta by 2. Sin theta by 2. Okay. So this thing, it's making some angle with this x-axis. Okay. So I have to take component of this also along x-axis. I cannot just leave out like that. But here in this case, this mg sin 30, it's perpendicular to this plane, which has got this line. So it's perpendicular to this line also. Okay. So since this mg cos theta is perpendicular to this line, I can neglect it. There is no component of this thing along this one. Okay, so this thing will not contribute. And once I come to this plane, again this component which I am neglecting is perpendicular to this line. Okay, so that's time I can leave this thing.
Yeah.
So you just cannot take components and then keep getting the thing. The one which you are leaving out, that should be perpendicular to the direction I'm interested in. Okay. So these two, one which I'm neglecting, they are perpendicular to the line of motion. Okay, one is perpendicular to the fold plane, another is perpendicular to the line of motion. Is it clear?
Yes, sir.
Okay. This one.
No, sir, I did not do this.
Okay, try. Will there be stretching in this spring?
Sir, which spring?
Both of them.
Okay.
Will there be any stretching?
Yes, sir.
Okay. And once I cut that string which is down, so will the stretching change immediately?
T2. If you cut T2, right?
Yeah, T2 is cut. So
Yeah.
immediately after it is cut, will the extension of the spring jump back to its unstretched length, or will it change?
Yes, sir, it will change. It will compress.
No, it will not change immediately. It will take a finite amount of time. So just after it is cut, the extension will remain same. Okay.
Okay.
Because spring is like a cushion, it will not change immediately.
Okay.
Okay.
Sir,
So
but in the question it's asking immediately, right? So it will be 0 then.
what is 0?
It's asking immediately in the question.
No, acceleration m4 it will not be 0 because tension is there at the top. No, velocity could be 0, but acceleration won't be 0. See,
Okay.
one thing is I can consider this whole thing as a system of single mass. This I can do. There is no internal motion in the masses of the masses. Okay. This spring is stretched. Immediately after it is cut, the stretching will not change. Just after it is cut, I can still consider this combination of M1 and M2 as a single system. Okay, and write the equation like this.
Okay, sir.
This is before it is cut. Okay, similarly, I can consider this M3 and M4 as a one single system and write the equation like this. Tensions T1 and T2 are different because T2 is a different string. So from this, I'll get T2 as this one because T1 I'll get from the first one. Okay, so this is before it is getting cut. That's why the acceleration is not moving. So the forces are equal. Acceleration is 0. And after it is cut, okay, after it is cut, see before it is cut, there was a force like this, right? T2 on this M4. right? After it is cut, the T2 is disappearing. So effectively, it's as if some T2 forces is acting upwards. Is it clear?
Okay.
Okay.
Yes, sir.
So that force is the one which will accelerate this mass M4. Just after it is
Yes, sir.
cut, the force acting on M4 is T2 because previously T2 was acting downwards, and with this down force, the net force was 0. Now this downward T2 force is removed, so there will be effective upward force of value T2. Okay, that T2 is acting on this mass M4, and that will give an acceleration of T2 by M4. Okay, and T2 value is being found like this. Okay, so I can consider a combination of M1, M2 and the spring K as a single mass if there is no internal motion inside. And before it is cut, there is no internal motion inside. So I can consider the forcing as one mass. If there is internal motion, you can consider as a single mass. Okay, the same is true for the other one, M3, M4 and the spring. So from this I get T2, and after it is cut, this T2 is disappearing, and before it was cut, the M4 with this force of T2 was rest, the net force was 0, and after this cut, since the T2 is disappearing, so effectively a force of T2 is appearing on the upward direction, which will give the acceleration to M4. Okay. So this is a unique problem which you should remember. Okay.
Yes, sir.
Okay. This one. You getting it?
Yes, sir. Sir, I think answer is D.
More than one correct answer.
Okay. Sir, answer is A, C, and D then.
A, B is also true.
Okay. Yes, sir. Yes. B is also true. All are true. Yeah. All are correct.
Right. So how did you do it? The acceleration of how did you constrain the accelerations of the blocks? It's a little bit.
Sir.
Okay. What I did is this one. This AC, no, let the acceleration of this thing be AC upwards. Yes.
Yes, sir.
And with respect to this pulley, okay, let the acceleration of VA be let the string move like this in the anti-clockwise direction way. Okay, so with respect to the ground, the acceleration of A will be A plus AC, and the acceleration of B will be A minus AC. Is that clear?
Yeah. Yes, sir.
Okay, and I draw the free body diagrams A, B, and C. A, B, and C. Okay, and I'm taking this case. There are two things that can happen. When A is going down, B may not leave the ground. This pulley will come down and C will go up.
Okay.
That is one possibility. Another possibility is C is remaining on the ground. When A is going down, B is going up. Okay. The third possibility is both B and C are going up. Right?
Yes.
there are three possibilities. A is definitely going down because that's what they are given. A is being 5 kg is being released. So either B can leave the ground, or C can leave the ground, or both can leave the ground. Okay, but from this value of the masses, B is 10 kg and C is 8 kg. So I'm assuming the case where C is leaving the ground and B is staying as it is. Okay, so I'm assuming this case. And when B is just about to leave the ground, C is about to leave the ground, the normal reaction on C will be 0.
Yes, sir.
Okay. And when this thing is not, B is not leaving the ground, the acceleration of B should be 0. So A minus AC is the acceleration of B. So A should be equal to AC.
Yeah.
Case one is B, C is leaving the ground and B is staying on the ground. Okay, so with this assumption, I can write the equations and solve the thing. And I'm getting a solution, and I'm getting the value of tension as 4G plus 20 by 7. So in this thing, on B, the downward force is 10G, and this tension is 6 point something into G. So this normal force is not 0. That means that P is not leaving the ground. So the solution is consistent with the assumption. Okay, so this is the case that is happening. Okay.
Yes.
So much of explanation is there. I don't know how you did it.
Sir, it's same way.
They're good in the solution, but there is no explanation there. Right?
Sir, I didn't see the solution.
Okay. Then what do you take as acceleration of B, A and B?
Wait.
Okay, because this is an important thing. You have to realize that A equal to AC, and acceleration of B is 0.
Okay.
This A is acceleration of the right. See, A is acceleration of A with respect to the pulley. So this is velocity of A minus velocity of pulley. So velocity of A is then A plus velocity of pulley, and velocity of pulley is same as velocity of C. So you get acceleration of A as A plus AC. Only with this understanding, you will get this one. Where A is the acceleration of the block A with respect to the pulley P. This is the pulley P. Okay, suppose I take a spring constant K, and I split it into two parts. Okay, so what is the spring constant of this one? Each one of them, both will be same, both are equal. So what is the spring constant of this one? Suppose I call this K1. How is K1 related to K? K is what the force.
No, sir.
F equal to K into X, right? So K is the force which is required to compress the length by one unit. K is actually change in length, which is actually delta X, which is change in the length of the natural length. Okay, and when delta X is 1, whatever the force required to change that length is the value of K. Okay, if K is more means then the more force is required to change the length by 1 unit. So K more means the spring is tight. Okay, and then we replace these two springs by, I'll connect two of these springs in series. Okay, and suppose if this extension of this one is X1 and apply the same force F here, applying the same force F here. Okay, if the extension of this half spring is x1, this is x2, and suppose this extension is x, can you relate x and x1, x2 to x2? I have to relate x, x1, x2. What is the relation? First of all, x1 and x2 will be same, right? Because both are equal halves.
Yeah.
Okay, and how we relate x to that x1 and x2? Is it clear? Because the points are same. Suppose I call this a point A, this is point B, this is point A, and this is point B. I'm applying the same force. Here also F. Okay, and x, right? Okay. So I'll divide by F throughout. What is x by F? From here, from this one, what do you get x by F as? 1 by P, right? Okay, this is 1 by K1 is 1 by K2, which is equal to 2 by K1 because K1 equal to K2 by symmetry. They are equal halves. Okay, so K1 is 2K. So when I make the spring smaller, it is going to be more tight. Okay. The need to understand this is, suppose I have a spring which has got say 10 turns or 10 coils, whatever you may say. And suppose I increase this length by 1 unit. So each turn, how much will it extend? 1 by 10, right? 1 by 10 centimeter per turn. Is that right? Because all the extensions will add, no? 1 centimeter is this extension between these 2 points. Okay, and there are totally 10 turns. So one turn will stretch by 1 by 10 centimeter. Is that right? Yes or no?
Yes, sir.
Okay, now if we take half of this spring, five turns, okay, and suppose I'm stretching by 1 centimeter again. How much will each turn stretch? 1 by 5, right? Okay, so getting this stretch is difficult, right? 1 by 5 centimeter per turn and 1 by 10 centimeter per turn. So this is tight spring. Because when number of turns is reducing, the contribution of each turn should increase to get the same extension. Right? So put it in other words, if the spring has got more turns, it's easy to compress or stretch it because each turn will share its load. Okay. So when the number of turns are decreasing, then the spring is becoming tighter. It's to create the same extension, I have to apply more force. Here the force will be F1, and here the force will be F2, and F2 will be 2F1. F1 will be 2F2. I have to apply more force to create the same amount of extension. Is it clear?
Yeah.
So if a spring has got lesser number of turns, it's more tight. So when I combine two springs in series, okay, the number of turns is increasing, right? So the combined spring will have a lesser K. K is a spring constant. If it is tight, means K is more. So that's why the shorter spring will have more K. Here it is 2K and this one is K, the combined spring. And the opposite is true for a parallel spring. If I spring like this, I split it into two. This is say length L. I split it into half L by 2 and L by 2. Okay. Now I'm applying the force F here between these 2 points. The points are same. The force is also same. So now this parallel combination, is it a tighter spring or a loose spring?
So
Okay. Suppose here the spring constant is K and here it is K1. Okay. So here F equal to K into X. Here, what is the force which is stretching the spring? F or something else?
F1.
How much is F1? It's F by 2. By symmetry, right? This is F1, this is F2, and F1 and F2 are same by symmetry because they are equal halves. So F1 is F by 2. This force will get, this is the force F, it will get divided between F1 and F2 equally. So F1 is F by 2. So to create the same extension here, okay, so K1 will be F is Kx by 2. So K1 is K by 2. So when you connect in parallel, this is a loose spring. K1. Okay, right. So when I connect two springs in series, the spring constant is decreasing. When I connect in parallel, spring constant is increasing. Is it clear? Right. The important step is when I connect in series, the extensions will add x equal to x1 plus x2. X equal to x1 plus x2. When connected in parallel, the forces will add F equal to F1 plus F2. F equal to F1 plus F2. That is the basic relation. From that, you will get the equivalent spring constant. This okay, you may not have, because this is a second playlist, circular motion. See, there is a spherical surface like this. Okay, so this is a circular track, and there is a mass on top of it. Okay, it's moving like this, and when it is about to leave contact, the normal reaction will be zero, right?
Yeah.
The forces acting on this mass are the weight mg, okay, and the centrifugal force mv square by r with the circular track, okay, and then the normal reaction. These are the three forces, okay. So this mg, I can take a component in this direction, okay. So when this component force matches with mv square by r, normal reaction will be 0. That is the point at which it will lose contact. Okay. Here I'm releasing with the speed of u, and u will constantly, velocity will constantly keep increasing. So it increases at this point such that mv square matches with this mg cos theta. This normal reaction will become 0. Okay. So at that point, you get the velocity as this one. Okay. This equation is clear, no?
Yes, sir.
Okay. So from that you get the velocity at the point at which it loses contact. So once I get this point at which the velocity is known here, I know the velocity here, so I can find this height h. Right? That is by
Yes, sir.
energy conservation, because the potential energy here is less than here by this mgh. So using this energy conservation, I can find the height h.
Okay.
Right. Okay. Any questions?
No, sir.
Go through the notes, and there are some.
Yeah.
These are all important concepts. You have to think that this thing, if this is x-axis, right? This one. This is x-axis. So I can transport it parallelly and say this is my x1 axis. Okay. And I can take this as y-axis. Okay. And this as z-axis. Okay. So this component mg cos which I'm neglecting is along z direction. Okay. And this